Okay, good morning, everyone. So let's see how many people have joined. Okay, so let me share the screen and so that we can just have a brief introduction. Okay, so can someone comment and tell me that is this slide visible where it is written 21 SPT 610 statistical mechanics? Okay, Tariq. Okay, okay, got it. Thank you. So let's very briefly see that what this course is going to be like, and then we will start doing some few things. And if any one of you want to speak up, then just message me and then I'll give the permission accordingly. I think by default I'll keep these settings that everyone will be able to speak. Okay, so that's okay. So yeah, so this is the going to be our course, and the introduction to this thing you already read in your graduation class also, that there you studied one course which called StatMech. Just a minute. It's called statistical physics, in fact, and thermodynamics, right? So that is I guess maybe BSc second year, or maybe first or second year, I don't know, depend upon from which university you are coming. So you have read this course in your lower class, so we are going to like build upon those basics. And this particular course I'm going to follow the textbook by RK Patharia. Although this everything is given in your course content, the course description part, in your Blackboard platform, everything is given in detail, and I have also provided you with all the soft copies of these books. So those are available for your download, so you can have them. And I also like added some reference PDFs as lecture notes, but you can also, you know, uh, see if that is useful, and later we will also keep on adding or updating that content as we move through the course. Okay, so the idea of this course, basically I'm mainly interested in telling you this this book is having a title StatMech, or statistical mechanics. So there is another book by Karsan Huang, and there is another book by Agarwal. So those are also nice books, but I will be strictly following this as my textbook. We can refer to others also if time will allow. Okay, so so let me talk about this continuous assessment. So this comprises of certain components. You already know this, that it has obviously your attendance. So how much marks each component is having, so that's given in your syllabus also, you can have a look, but I'm interested in telling you that what components are there. Okay, so then your attendance, and this is based on whatever your percentage attendance you acquire in this course. At the end, examination department directly give this marks, I think, out of 2. So these things you have to see, right? Then we are also going to conduct a couple of quizzes, 2 quiz per unit. So this I will announce the dates of these in very well advance. Okay, so because there are 3 units, so we are going to having 6 tests roughly at alternate weeks. Then this is one of the major things, the term paper thing. So this particular thing, now you might have experience with me that okay, let me finish this. I think this thing has most weightage as far as I remember. So this is most weight of this guy, and then we also have some presentation kind of thing. So this we have to still figure out that how we are going to conduct this online. I hope things become physical, because only 40-minute lecture is there. So I have to see, because if I assume that there are 90 people, so even if I am giving 5 minutes to each person, so this is going to consume my 10 minutes in every lecture. So that I'm not going to this is going to be like this need to be worked out. Okay, so I'll tell you how we are going to talk about this presentation. uh, Last time we did not have, but that definitely will do. This is obviously very important. Then presentations, quizzes, term papers, I think they are mostly make up your continuous assessment. So the most important thing for me is, and you, most of you are aware of this thing, that don't try to copy. This is the single rule of my class. Don't copy. Okay, if you are, you many of you did this thing last semester also, and you got the results also. So this is going to be a very strict rule of this class. Other than this, I'm going to be a bit accommodating on quizzes or everything, maybe flexible with the date of submission. That's also possible, but you should adhere to the dates. And I also added a term paper topic as well as presentation topics on Blackboard, but I will be modifying them, maybe adding more or maybe removing some of them, so that I will announce very well in advance. Okay, so any question till now, if you want to ask, you may type in chat, or if you want to speak, that's let me message. Nothing. Okay. Or you may send your query in WhatsApp also, right? That's okay. We have that group. And okay. Okay, good, Nishta. So the idea is roughly 19 people I can see they are online. It means most of, because this class I know it is more than of 90 students. So it means maximum of you might be, your classmates might be not able to log in today, maybe due to not registering, pending documents, pending news. There can be n number of reasons. But my idea is I will be uploading these lectures recorded. Uh, okay, Tariq, this you have to email your HOD, right? Because he has control over these issues over timetable, right? This is beyond my control. So my idea is to provide material to those guys who are missing somehow today. So these lectures are recorded, as you know, every time. So I will be uploading it on OneDrive. They are available here on Blackboard also. So I will give link to Blackboard, OneDrive also, right? So okay, Nishta, just email, ask all those students to email the HOD physics. They are responsible to manage these things, right? It's their responsibility. So the idea is that actually this should not happen. If it is a lecture class, full class has to be here. Okay, please email, ask everybody whosoever facing problems to email the HOD physics, right, to correct their timetable. Although you guys should have contacted your HOD before this lecture also, because timetable is visible from long ago. Anyway, so I'm saying that these are recorded. OneDrive link I will give you on Blackboard as well as in group also. So just share that with everyone, right, so that they can listen this lecture at least today. So this is going to be very packed stuff, because we have to cover so many things. Okay, so let's these are the things. Okay, let's come to our topic, what we are interested in discussing today. So I'm basically interested in discussing this statistical statistical mechanics part, right? That's what our subject entitled. So first you must understand that this title has two different names. One is statistical, which essentially comes from the term statistics, and this mechanical or mechanics is coming from mechanics. More correctly, I would say the system dynamics or system dynamics, right? So what do I mean by a system dynamics is basically you might have read about this thing in your 10 plus 2 also, something called kinetic theory of gases, right? So kinetic theory of gases kind of thing. Don't worry about this writing, right? So I will be providing you notes which are basically a summarization of your book, so that I will be providing this time. Last time I was using on board, but this time I thought I will be using stylus with notes because of this clarity issue. Sometimes that board gets blurred, so we don't want to do that. Okay, so once you come on campus physically, which I hope soon that will happen, so then everything will be good. Okay, so this kinetic theory of gases, basically you are following the motion of the individual particle individually, then writing about their kinetic energy, potential energy, then writing about the equation of motion. In fact, all that Hamiltonian formalism, Lagrangian formalism, Hamilton Jacobi formalism, that can be applied to get these solution of these problems, right? Statistics is basically a branch of mathematics. So this is basically a branch of maths. I don't know if you remember this. This basically is just counting individual numbers, just counting particles. Counting particles, just a minute. Particles, then you can think of calculating probabilities. The stylus is a bit tricky to handle something. Okay, I'll get used to calculating probabilities and so on. So this all comes under statistics. So they look basically a bit different, but there is a very a kind of a strong connection between these two. Let me see, I wrote few things about this. Yeah, so as I said, so the kinetic theory of gases was a different branch of basically physics, right? So which was very well developed somewhere in 1850 by various scientists, and then there was an independent branch of physics, which is basically thermodynamics. More correctly, I should call this as classical thermodynamics, right? So then this thermodynamics, so mainly this work was done by this Carnot. You might remember that Carnot engine is there, Carnot cycles are there in thermodynamics, then experiments by Joule, right? Then Clausius, then Kelvin. All these guys contributed a lot in building the basics of this classical thermodynamics. But these were two independent things. And also thermodynamics deal with the macroscopic behavior of your matter, right? Macroscopic behavior means I'm talking about, suppose you talk about temperature, volume, right? Energy. Here you are not talking about the individual particles, or maybe you can talk about Gibbs free energy, then enthalpy, Helmholtz free energy, so on. So these are the quantities which are basically telling you the macroscopic behavior, not microscopic. So you are not talking about individual particles. Okay, so you are basically dealing with bulk material. This thermodynamics does that. So later we'll see when we'll modify this classical version of thermodynamics to the quantum version. We are basically going to touch individual particles also. Okay, so in fact people talk about the temperature of single atom also. Okay, so then similarly this, as I just told you, that this is based on the dynamics of gaseous system, because this is a kinetic theory of gases. This is in general for any matter, right? You will see we can also apply these on black body radiations or black holes, right? Or neutron stars, so on. So this is not restricted to only gases, but theory of gases basically was mainly related to these gases. So I'm also thinking that if you are messaging me something. Okay, so you're listening. Good. You can message me, okay? If have any doubt. And next time, next class onward, I'll just keep the permission such that you can unmute and speak without any. intervention by me. Okay, so then this was an important step that in 1872 this Boltzmann he proposed some H theorem. Basically, theorem what he did, he basically related the entropy. This is basically a thermodynamical property. Entropy, you know, usually we represent by this S, and this is what you would should say that it is a measure of disorder in a system, right? So that's being measured by parameter S. So what Boltzmann's H theorem did, he basically related this entropy, which is a thermodynamical property, with the molecular dynamics, which is basically based on kinetic theory of gases. So he proposed this relation via this H theorem. So this was a kind of a building block between you can say thermodynamics and mechanics, which is basically statistic of particles. Okay, so then which this is the part we are going to focus upon. Kinetic theories of gases, it is like further upgraded, and the more advanced version of this earlier versions of 1850 was further modified to this ensemble theory. We are going to see various type of ensembles. So quickly to name them, I would say one is called microcanonical ensemble, then there is canonical ensemble, and third one is I think grand canonical ensemble. But we'll jump to them after discussing very basic and simple things, just to appreciate that what this link I mean to. Okay, so what Boltzmann basically derived without going into much detail. So easy. It's just to like appreciate the beauty of this link, that how my statistic is linked with the thermodynamics. Okay, so the results from this statistic and mechanics, they are basically the thermodynamics of the system are going to be followed if you try to link statistics with the mechanics. I hope you understand statistic, as I just said. So this is just calculating the probabilities of individual particles, then how they are moving, and mechanics basically, sorry to say, mechanics is basically how, but what's the dynamics. Okay, here so in statistic this is more about the counting number of possibilities and probabilities. So and if we try to link them up, so this thermodynamics is just a consequence of that link. So this is what we are going to, or how I justify the title of the subject, the statistical mechanics. Okay, okay, so now just to begin with, any question till now if you want to ask? Let me see if any message I received. No. Okay, so let me quickly go to this thing. So now what I'm interested in, that I'm interested in defining these two terms. One is called macroscopic and microscopic states, or generally it is also called macrostate. Macroscopic states means a macrostate. I'll tell you what is the meaning of a macrostate. Okay, and then another is microstates. What do you mean by this? Okay, just to understand this, let's have some physical scenario. So I'm having a physical system. I think there is one message. I thought they are actually attending other classes, sir. Can we tell them statistical mechanics is a thermodynamics at the quantum level? Tariq, it's okay. If they are attending other classes due to some problem in the timetable, that's okay, because of course they are not going to get the attendance. All of you know that I am not compromising on those things, but this is the class they are supposed to attend. And the second thing is that they can watch this video lecture, as I just said, recorded version, right? So if they will get attendance there, that's fine. So no need to now communicate during the lecture. Okay. Okay, so I was saying, so I'm going to consider one's physical system, uh, and let the total number of particle in the system, and the important term here is identical particles. So I'm having n identical particles which are confined to certain volume V, and total energy of the system I'm representing that by E, right? So now just to give you some idea, this n is usually very large. You know that if I'm having 1 mole of one a certain material, then I have Avogadro number of particles, that's 6.023, I think, 10 raised to power 23. So these many particles are there. So you know this n is actually very, very large. Okay, And usually volume, if you talk about the gas occupying certain volume, this volume is also going to be a very large kind of thing. So typically what we say this thing, that when we are doing the calculations, and we also term this as thermodynamic limit. So my number of particles of my physical system, usually they tend to infinity. Volume is also infinite, doesn't mean that it is occupying full volume of the universe. It means it's very large, right? Although finite, but very large, but in such a way that this n by v ratio is a constant thing. Okay, so this n, what we call as particle density, this is going to be a constant. So particle density, I can always you can say fix, for example, density of oxygen in a cylinder, I can pre-decide, right? I can fix that at certain value. Although number of particle can be very large, so I can make the container equal to suppose a swimming pool, and volume is very big, number of particles are very big, but particle density is fixed. Okay, so in such a scenario, so these extensive property like temperature, right, pressure, then your what I should say, volume actually is a parameter. So these extensive properties, they become function of number of particles or volume. Higher the number, higher the volume, my property will be bigger, kind of thing. Okay, so then there are other properties which generally are named as in actually this should not be there. Just a minute. Yeah, temperature is not a extensive property. In fact, energy is. Okay, so then there are intensive property which doesn't depend upon this number of particles or volume. Okay, for example, density. Density of particle doesn't depend upon n or v, because make n larger, v larger, but ratio is going to be same. Okay, so this we see in more detail later also. Okay, now, because I was interested, or I am interested in explaining these concepts to you, macrostates and microstate. Okay. Now, suppose as I define this system, the physical system with n number of particles having total energy E, occupying a volume V. So then I'm saying that if suppose there are different energy levels, for example, we can consider this also. Although this energy can be discrete also, or it can be variable also. Suppose E1, E2, E3, and so on. And suppose there are N1 particle at level E1, and suppose there are N2 particle at level E2, and so on. So I think you will agree with me that this is going to be total energy, right? So Ni particle multiply the respective energy and sum over all the states. So I will get the total energy. So this is one constraint which is going to be followed by that system which I considered above. And of course, I am talking about non-interacting particles, because if there is certain interaction energy, so then that term will also get added. Suppose Eij, so my ith and jth particles are interacting, then there will be interaction energy term also. But that, for simplicity, I'm not considering right now. We're just assuming simple things. And I think you will also agree that total number of particles will be sum of all the particles in these all levels, right? So this is also not very big thing to understand. And so n is the total number of particle, E is the total energy, right? And V is the volume occupied by them. Basically, if you tell me these three parameters, then the state of system will have certain specification which is being specified by these numbers, number n, v, and e. Basically this specification I termed as macrostate. Macrostate. So suppose if you change your n to n dash, you change your number of particles keeping v and e same, so my macrostate will change, right? This is the macroscopic behavior of the system is going to change. Now suppose if you have your so this is how you define your macrostate. Okay, now suppose if you have your macrostate fixed, like you describe a macrostate with nve. So basically this is a, or in literature you will see something like this. So the macrostate is defined like this, nve, and by now you must understand this is number of particle in the system having total energy E, following this constraint, and occupying a volume in space V. So this is the how you define a microstate. Now idea is, so do you think that for this microstate only one possible configuration of these number of particles in these energy levels will be there? No, there can be more than I would say number of possible permutations in which you can arrange these Ni particles among Ei energy level such that this summation becomes equals to E, right? So you can arrange, so for example, a two particle here, three particle here, maybe one particle here, seven particle there, and so on. Maybe some of the energies may be negative, positive. That may also, some of them may also be zero, so that you do this summation and you get this energy E. Now you change these permutations. Suppose here now you put one particle, then maybe one particle, three particle, and so on, in such a way that this sum again comes out to be same energy. So there can be actually in principle large number of possibilities which satisfy constraint number one as well as two. Two will always be satisfied, only is the rearrangement in energy levels. Okay, so all these different various permutations or combinations or different ways of rearranging the particles amongst different energy levels corresponding to same macrostate are called microstates, right? So those are called microstates. So a given macrostate can have a large number of microstates. And further, a couple of comments I would say. So if you look classically, then your volume is usually very large because we are dealing with the macroscopic or bulk material. So then your these energy levels or energy eigenvalues, they are very closely spaced, or ideally I would say they are basically continuous function of energy, right? But you know, if you jump to quantum mechanical case, then this can be discrete energy levels, right? For example, if you remember your harmonic oscillator kind of thing, so energy level of, okay, because we are using symbol I, so let's use I. So energy of ith level, okay, let me even correct it more. So these EI which are appearing here, so these are basically I plus half h bar omega, right? So these are the energy levels of harmonic oscillators, and these are discrete, equally spaced but discrete. So there is a gap between this. But similarly, you also have energy level, energy eigenvalues for particle in a box, and maybe so on kind of thing. And particle in a box, if you remember, so as you go up, the spacing between the energy levels keep on decreasing. So if you make your n very large, then this spacing between the energy levels, it keeps on decreasing. So that's what I'm saying. Then you approach basically classical limit. Okay, so and of course this volume, due to dependence of energy eigenvalues on volume, comes into this dependency in the description of macrostate, because energy is being decided by how much volume is being occupied by the system. Okay, so now what we can do with this, so this is basically, I already said about this. So for a given macrostate, a large number of possibilities at a particle level to distribute energy E amongst n particles occupying space V. So each such distinct way of, there is a spelling mistake here, describing, so there should be R, describing same macrostate is called microstate or complexion. Okay, so this is a term being given in your textbook. Let me see any other message. No, not yet. Okay. Yeah. So this example you might remember, you people have done in your BSc also, distributing. For example, you have three particle in two boxes. I'm just going to give you example, two boxes, right? So that you just recall. So I have two boxes. What are the possible ways so that I can distribute these particles? So you can put three particle in one box and leave other empty. Or you can put two particle here, one there. Or you can do one particle here, two particle there. You can't do half and half, right? So that's not possible. So then you can put 0 particle there and 3 particles there. And if you see this 3 is number, so this is your n related to, right? And 2 is basically related to volume. So boxes are related to your volume. So you defined your macrostate, you defined this n to be 3, and this is volume is proportional to 2. So if you define the volume of one, suppose box as a v naught, so then total volume will be 2 v naught kind of thing, right? So this is the definition of your macrostate. But all these four combination, 1 2 3 4, so these four are basically your are the number of microstates, right? But we have to make this condition on these distribution that this also remains same. The summation of ni into ei, this always remains same. So that we are distributing these particle in such a way that the energy sum. So this box must be associated with some energy. If I'm putting particle in this box, this must be associated with certain energy. Then I can calculate the sum of this total energy. Similarly, in this distribution, in every microstate, energy should be E, because this has to be in the description of macrostate. So hope this is clear that what's the difference between macrostate and microstate. Although this is a concept from your lower class, right? Okay, so this is also an important aspect, because for a given macrostate, which is NVE, there are large number of microstates. So this microstate is usually represented by this symbol omega. It's capital omega, right? So NVE. For example, this NVE, this was equals to 4 for this example, because there are only 1, 2, 3, 4 microstates for this. So this is basically just representing that corresponding to this macrostate, NVE, how many microstates are there. So because for a given macrostate, NVE, there can be very large. So this omega, we will see in later lectures that this is a very large number, very large. Just for example, I showed here 4 distribution, but this in general is going to be very large. So there are very large number of microstate accessible to the system for same macrostate. Okay, so all the microstates, they have equal probability to be occupied by the system. So this is one very important aspect of what you say, I would say, of this link between statistical and thermodynamics, that all the microstates have very similar, or I would say equal probability being occupied by the system or by the macrostate. So this principle is basically termed usually in literature as principle of equal a priori probability. And later we will also see actually this is not true. Okay, but you must know. So yeah, as I already told you, I think we are left with around 5.5 minutes. So I think I'll wind up. So this, do remember, okay, it's very easy to get confused with the symbols, but if you are just following what I'm saying, or if you just rewatch the lecture video recording, then you will follow immediately, and definitely you are supposed to read the textbook. Okay, and I hope you people are buying at least one textbook every semester per subject. You have to buy. These are hardly going to cost you 500 or 600. That's not more than the net pack which you people recharge every other month. Okay, so you should make a habit, because reading from textbook is best. Many of you might not have the laptops, so reading on mobile is going to strain your eyes, and that's not a good way to learn. Okay, so yeah, if you are going to read the book which I just mentioned in the starting of the lecture by RK Patharia, Statistical Mechanics, so then you are going to appreciate what I am discussing, because I am following that particular book exactly as we did last time with the Goldstein. Sir, can you please upload the PDF? Nishta, I already said I uploaded all the books on BB. Okay, have a look into the content in the BB, and if you don't find, then tell me. Okay, so everything is being uploaded for your help. I prepared this course as good as I can, but I'll improve it further. Okay, so let's come back to thing. Yeah, this thing I already told you that n will enter in the number of microstates, because how many particles, that is going to decide how many number of possible microstates are there. Suppose if I give you one particle only, then it is different situation. For example, here, right? So if I give you only one particle, so only two combination can be there, 1 0 0 1. So your number of microstate changes, right? So if I give you suppose 8 particles, so then you see these number of distribution are going to change. So this parameter or number of microstate in a given macrostate changes with n, or it depends upon n. Definitely it also depends upon energy, because that is going to constrain that you are not allowed to have every microstate, only which is going to satisfy this condition, that ni, energy of ith level, going to be sum over i's, give you total energy E. Only those are the allowed microstates. And volume, obviously, as I just told you earlier, that this comes because these energy eigenvalues depend upon volume. Okay, this you can very easily see from your particle in a box kind of thing, where you have L square in the denominator. So L square is equal to L is the length of the cubical box. So L square is basically volume raised to power 3 by 2 kind of thing. Okay, so this volume comes into the picture via energy. Yeah, as I said, you can see the example. So once I have this parameter, which is the number of microstate for a given macrostate, then I can in principle drive full thermodynamics of my system under consideration. And you will see mostly in this course we will be doing this. For various system we will be driving the number of microstates for a given system, be it a microcanonical ensemble, canonical ensemble, or grand canonical ensemble. I will always be calculating this number, and once I have this, then I can drive the thermodynamics. There is a link between this omega and the thermodynamical parameter, in fact, the entropy, right? So if I establish that relation, then I will always be able to drive this thermodynamics of the whole system. Okay, so we'll be doing some examples with that also. Okay, so I think there are a couple of minutes left. So I will start with this topic, which is going to help me establish the relation between entropy and this number of microstate, which is basically the physical significance of this number, the number of microstate, or basically I would say the statistics of the system. It's nothing but statistics, right? Hope you now can appreciate that this parameter is related to the statistics of the system under consideration. So from this I can drive the entropy expression. Once I have that, then we are in good position to appreciate the beauty link between statistical mechanics as well as thermodynamics. Okay, and that's what I think most of you people did in your BSc also. I don't know if you were able to appreciate the beauty or link between these laws or not. Okay, but anyway, this part I'm not going to touch now. I will start, although I planned, but just in the introduction we spent some time, so I will continue it tomorrow, no problem, right? So I will stop here, and these PPTs, means with all this rough work, these will be uploaded in your Blackboard platform. Okay, so just before leaving, any of you have any question? I'm waiting. Anyone have any question? Please make a habit of asking question, right? Ask a lot of question, please. So that's the only way you are going to learn. I requested you people last time also, but and this time also, again I'm asking that make it a habit to ask questions. And why this? Why, sir? Can we tell that statistical mechanics is the thermodynamics at a quantum level? Statistical mechanics, no, Tariq, it's not like this. It's not like this. Statistical mechanics, I think you will be means in a state to understand this. This is a good question, in fact, right? So statistical mechanics is something else. Thermodynamics is, it's not basically, I would say, property of individual particles. Okay, so thermodynamics historically it is meant to be a macroscopic or for a bulk system. And for a bulk system we don't talk about quantum mechanics, right? Quantum mechanics is when we are dealing with the quantum particles or at microscopic levels. But there is a strong link. Okay, so we are going to, in fact, first in, I think, first till midterm your MST, we are going to talk about classical statistical mechanics, or this whole ensemble theory. Then after that we are going to jump into the quantum statistical mechanics, right? So I, again, as I said, we are always driving this number, the number of microstate, be it classical statistical mechanics, be it quantum statistical mechanics. But always from these expression of number of microstate, we will be able to generate the respective thermodynamics. Okay, so now you can think of whether that is quantum thermodynamics. Yes, there is a branch that's called quantum thermodynamics. Okay, if you are deriving the expression for number of microstates from quantum perspective, which we are going to do after MSc1. Okay, but you will get the answer to this question, or actually this question is bit incorrect, but that's fine, right? I think that's enough for today. Uh, so thank you everyone. Now you may leave, and I'll upload, as I said, this on OneDrive. Okay, thank you.